This is a lecture on a type of curve fitting called B-splines. The type of B-splines that we will talk about here is based on the book Applied Numerical Analysis written by Gerald and Wheatley. For this lecture, a segment of the B-spline curve will be based on 4 points and takes on a parametric form. If the first segment is given by capital B1 of t, then capital B1 of t is given by this equation. Lowercase b1, b2, b3, and b4 are all scalar functions of a parameter t. And p1, p2, p3, and p4 are the 4 points on which capital B1 will be based. The parametric curve capital B1 will lie on what is called the convex hull of the 4 points. The convex hull for the 4 points is the smallest convex polygon that will contain all the possible segments determined by the points. The 4 points happen to be the vertices of the quadrilateral. The parameter t is between 0 and 1. And for each value of t between 0 and 1, there corresponds a point within the convex hull of the 4 points. Let us see what capital B1 looks like by starting t at 0 and then dragging t all the way up to 1. Let's get back to the main reason for this lecture, and that is to find formulas for these scalar functions. With 4 points defining capital B sub 1, little b sub 1, little b sub 2, little b sub 3, and little b sub 4 will be third degree or cubic polynomials in T. We write this out in matrix form by separating the powers of T from the little a sub ij's. We will also write out capital B sub 1 as a matrix product. In fact, it is a dot product. A dot product is sometimes written as a matrix product. In this case, it is the product of the row vector b1, b2, b3, and b4, and the column vector capital P1, p2, p3, and p4. Now, this row vector is the transpose of this column vector. And so we take the transpose of this entire equation so that this column vector becomes a row vector. This is then equal to the transpose of this product on the right side. And to get the transpose of this product, we have to get the transpose of this column vector first, getting a row vector. And then we get the transpose of this matrix. Recall that when taking the transpose of a matrix product, we take the transpose of the factors, but we have to reverse the factors in the final result. The only thing missing in the formula for capital B1 is this vector of points P1, P2, P3, P4. And so capital B1 is given by this matrix product. Our attention now turns to the entries of this matrix. The entries are supposed to be real and constant. To find the values of these entries, we turn to the geometry of the B-spline. We will need the second segment of the B-spline, which we call capital B sub 2. Capital B sub 2 looks like capital B sub 1, except that capital B sub 2 uses the points P2 to P sub 5. And so we introduce P sub 5 into the diagram. Like capital B sub 1, capital B sub 2 will lie in the convex hull of the 4 points that it uses for its formulation. The parameter t for capital B sub 2 still lies on the interval from 0 to 1. Dragging t from 0 to 1, we generate capital B sub 2. We will use a computer software to help us figure out what the values are of the entries of the 4x4 matrix. First, we define capital B sub 1 of t. we have the row vectors of the powers of t, and then we have the 4 by 4 matrix. And then we have the column vector of points. We need to examine what happens at the junction point between capital B1 and capital B2, so we also need the formulation for capital B2. Capital B2 is almost identical to capital B1. The only difference is that we increase the indices of the points by 1 for capital B2. Capital B1 ends at the junction point, and this is where capital B2 begins. And so B1 of 1 should be the same as B2 of 0. Evaluating all of these, we get the formulations for B1 of 1 and B2 of 0. Now these two expressions give the coordinates to the junction point and should be equal. But note the absence of any P sub 5 term in capital B sub 1 of 1. But that's just to be expected, since B1 of 1 depends only on P sub 1 to P sub 4. But if these two expressions are to be equal, then B sub 2 of 0 should also not have a P sub 5 term, and so A sub 4 must be equal to 0. And we modify the matrix with this information. Using this slightly improved version of the matrix, we take a look at B sub 1 prime of 1 and B sub 2 prime of 0, and we evaluate these two quantities. These two expressions are supposed to be equal. What that means is that the two segments capital B1 and capital B2 meet smoothly at the junction point, or that there is a tangent line at that point. Note again the absence of any P5 terms in B sub 1 prime of 1. The same should be true for B sub 2 prime of 0. So A sub 3 must be 0, and we use this information for our matrix. We also require that the second derivatives match at the junction point, and so using the new improved version of the matrix, we calculate B sub 1 double prime at 1, B sub 2 double prime at 0. Cutting the discussion short a little bit and using a similar reasoning, we conclude that A sub 2 is equal to 0. Looking at the matrix, we now have just 13 unknowns, and so we need 13 equations in order to be able to solve for these unknowns. First, we go back to the continuity equation using the new improved versions of our matrix. Continuity means B1 of 1 equals B2 of 0. Evaluating, and then equating, we find some of the equations by matching point by point. P1 is absent in capital B2, and so this P1 coefficient must be 0. So that is our first equation. A sub 1 plus A sub 2 plus A sub 3 plus A sub 4 is equal to 0. This P2 coefficient should match this P2 coefficient in capital B2. This P3 coefficient should match this P3 coefficient. And A sub 1 should equal A sub 4. For the next set of equations, we take a look at the first derivatives again. P1 is missing from B2 prime of 0, so this P1 coefficient must be 0. This P2 coefficient must equal A13. This P3 coefficient must equal A23. For the eighth equation, 3A41 must equal A33. Now we take a look at the second derivatives at the junction point. Again, P1 is missing from B2, so this should be equal to 0. This P2 coefficient should equal to A12. This P3 coefficient should equal to A22. And finally, 6A41 should equal to A32. If we count the number of equations, we'll find out that there are only 12 equations, which is a problem because we have 13 unknowns, and this means that we need 13 equations. To supply the missing equation, we will have to take a look at the geometry of capital B1 a little bit more closely. In the figure on the right side of the screen, the 4 points are drawn to be distinct, but they don't have to be different points. Watch what happens to the point corresponding to capital B1 when we make P4 the same as P1, P3 the same as P1, and P2 the same as P1. Capital B1 of T ends up being the same as P1. This is true regardless of the value of T. And in particular, B1 of 0 is equal to P1. So going back to the formulation of capital B1, changing all the points so that all the points are equal to capital P1. We don't need B2 here. Evaluating B1 at 0, we should get P1. So this, which is B1 of 0, must be equal to P1. And so the 13th equation is A14 plus A24 plus A34 equals 1. To complete this solve command, we put in the unknowns, and we're just about ready to evaluate this command. And this is the result. Plugging these values into the matrix and recalling that these 3 entries are all equal to 0, this is what B1 of T looks like. And multiplying this out, we get the expanded form of capital B1 of T.